Hi folks, now that we've learned a bit about how the periodic table is organized, let's look at the information that the periodic table actually gives us. So each cell on the periodic table contains information about each element. And the first thing to notice is the element symbol. The element symbol can be one letter or can be two letters, but the first letter is always capitalized and the second letter is always lowercase. This is important because you always know that you have a new element symbol when you see a new capital letter. So in this example, I have just one element. That element is cobalt because there's just one capital letter. But here, this is a compound that contains two elements, and I know this because there are two capital letters here. This is carbon monoxide. So capital letters are important in element symbols, and you will be marked wrong if you're using capital and lowercase letters inappropriately because it does change the meaning of what you're writing down. Some elements have unexpected element symbols. So sodium, for instance, is not anything to do with the letter S. The abbreviation is Na. Potassium is abbreviated with a K. Copper is Cu. There are a lot of elements that begin with the letter C, and so just don't get them confused with each other. Iron is Fe. Silver is Ag, and gold is Au. So be aware of some of these commonly used elements that don't have the expected element symbol. The next piece of information that you always see in a periodic table is the atomic number. And the atomic number gives us the number of protons that are in the nucleus of the atom. This is important because the number of protons defines the element. All atoms of mercury always have 80 protons, and if you have an atom with 80 protons, it must be mercury. It's definition of what the atom is. This is sometimes also called the nuclear charge because it's all of the particles in the nucleus are protons and neutrons. Neutrons don't have a charge, only protons do. And so all of the charge in the nucleus comes from the protons. Remember that protons equals electrons in a neutral atom. If your positive and negative charges balance out, overall your atom has no charge. The next important piece of information that you'll see on a periodic table is the average mass, which is also called the atomic mass. This is always going to be a decimal number because it is a weighted average of the relative abundances of all of the different isotopes that exist of that element. So in the example of chlorine, for instance, most chlorine atoms have a mass of 35. Some chlorine atoms, about 25%, have a mass of 37. And so if I were to just average 35 and 37, my average would be 36. But this isn't a regular average, this is a weighted average. We take into account that there is more of the 35 mass isotope than the 37 mass isotope. So the average is closer to 35. And so if we do 35 times 75% written as a decimal, 0.75, and add that to 37 times its percentage written as a decimal, 0.24, and we add that up, we get 35.47 as our weighted average for the mass. And that's pretty close to what the value you see on the periodic table is. It doesn't match exactly just because there are other isotopes besides the 35 and the 37, and also because the mass isn't exactly 35 and exactly 37. But that's the general principle of how to do a weighted average that takes the percentages into account. So with all of that important information, the symbol, the atomic number, and the average mass, we can actually derive quite a bit of information about atoms using this information, especially if we combine this with the knowledge of atomic structure that we've already learned. So, just to refresh your memory about what we've learned about protons, neutrons, electrons, as well as some new information that will help us as we move forward. Kind of fill in this table as we go on, and I give you information about the different subatomic particles. First of all, electrons. Remember, electrons are not in the nucleus. They're found in the electron cloud outside the nucleus. They have a charge of -1, and while they are particles and they do have mass, that mass is so negligible we basically ignore it. So we say that it has a mass of 0 AMU, where AMU stands for atomic mass units. These are special units that we've created for talking about atoms, because if we used units that are more familiar for talking about mass, like grams or kilograms, you can see that we have extremely small values here for the mass. These numbers are cumbersome and difficult to work with because the scientific notation is so small. So we did invent a mass system of measurement specifically for measuring masses at the atomic and molecular scale. Protons have a positive charge. They are located in the nucleus of the atom, and they have a charge of, oh, I've already said they have a charge of +1, but we say that they have a mass of 1. And you can see that compared to the electrons that we've looked at, they are orders of magnitude more massive than the electrons, which is why we basically ignore the electrons. Neutrons have a charge of 0 and a mass of 1 atomic mass unit. If you look at their actual mass in kilograms, they are just slightly more massive than a proton, but for all intents and purposes, they're approximately the same mass, and so for simplicity, we do just say that both protons and neutrons have a mass of 1 atomic mass unit. So filling in your table should look like this at the end. So, can atoms be changed? What happens in chemical reactions? How do the atoms change in these chemical reactions? Some aspects of atoms can be changed and other aspects cannot, or at least not in a normal chemical reaction. For instance, changing the protons changes the elements. That is not something that happens simply because protons are protected deep inside of the atom. So they are in the nucleus, they are hard to reach, so it doesn't easily change. The only time the number of protons changes is in the course of a nuclear reaction. It's in the nucleus, that's why it's called a nuclear reaction. If you did change the protons, not only would you change the element, but protons have mass and protons have charge. So you would also be changing the mass and the charge of an atom. How about if you change the neutrons? Can you change the neutrons? Once again, the neutrons are in the nucleus, and so they are hard to reach. But if you change the neutrons, you do change the mass of the atom. As I said, they're in the nucleus, are hard to reach, so once again, changing the neutrons is something that only happens in a nuclear reaction, not a chemical reaction. And this creates isotopes. Isotopes are atoms of the same element with different mass numbers. So if you've got 2 atoms of the same element, but with different mass numbers, you've got 2 different isotopes of the element. What is a mass number? Since I just used a definition that says mass number, I better tell you what a mass number is. The mass number is the number of protons plus the number of neutrons. Remember, these have a mass of 1 AMU, and these have a mass of 1 AMU, and electrons are so have so little mass that we don't include them in the calculation. We say that they have a mass of 0. So if you add up all the protons, all the neutrons, that gives you the mass of the atom. This is always going to be a whole number. You can't have 1.5 protons or 2.75 neutrons. So this is always going to be a whole number. Unlike atomic mass, that mass that was on the periodic table, that's a decimal number because it was an average. Here, mass number is always going to be a whole number. What happens if you change electrons? Well, if you change electrons, that changes the charge. And this does happen all the time in chemical reactions because unlike protons and neutrons, electrons are here in the energy levels that surround the nucleus. These are easy to reach, especially the valence electrons. And valence electrons are electrons in this very highest energy, the most outer energy level surrounding the nucleus. So those electrons are easiest to reach and easiest to change. It's hard to reach electrons that are in lower energy levels. So these ones on the outside are valence electrons, and the ones on the inside here are called core electrons. Those electrons are harder to reach, harder to change. They do not change easily. If you change the number of electrons in an atom, you're changing its charge. So you are creating an ion, which is an atom or a molecule with a charge. You can calculate charge by doing protons minus electrons, and if protons equals the electrons, then your charge is 0 because you're subtracting two numbers with the same value, like 6 minus 6 is 0. So an atom with 6 protons, 6 electrons would have a charge of 0. So how can we use this information about protons, neutrons, and electrons, which we can pull off of the periodic table, a lot of this information? How do we use that information to draw models of elements? So for any element, the period number, which horizontal row the element is in, tells us how many energy levels, kind of rings or shells, of electrons to draw around the nucleus. Energy level 1 holds up to 2 electrons because period 1 in the periodic table has just 2 elements in it. The shape of the periodic table reflects electron configurations. Energy level 2 corresponds to period 2 on the periodic table, and energy level 2 has 8 elements across, starting with lithium and going all the way to neon. Therefore, energy level 2 holds up to 8 electrons. This is a simplification. We're going to learn more about electron configurations later, but for now, we're going to say that periods 3 onwards also hold up to 8 electrons. In reality, they have 8 valence electrons, but hold more electrons than that. We'll come back to that later. But 8 is a special number when it comes to electron configurations because an energy level is considered full with 8 electrons. The exception to that is energy level 1, which is full with just 2 electrons. That first energy level is very close to the nucleus. It's not big enough to hold more electrons. This idea of an energy level holding 8 electrons maximum, that's called the octet rule. Oct as in octopus or octagon, meaning 8. We call it the octet rule because these energy levels are holding 8 electrons. Another important thing to know about Bohr models is that lower energy levels fill first. So you put electrons in energy levels that are close to the nucleus before you start putting electrons in energy levels that are further from the nucleus. So let's look at an example like sodium. This is the correct Bohr electron configuration for sodium, and let's talk about why. So sodium, when I look at the periodic table, is in period 3. And so we're going to have 1, 2, 3 energy levels outside of the nucleus. I see that sodium has 11 protons, and because I'm drawing a neutral atom, I also am going to want to draw 11 electrons. As I said, we need 3 energy levels of electrons. And so now, remember I said energy level 1 can hold 2 electrons. 1, 2. Energy level 2 can hold 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And then energy level 3 could hold 8 electrons, but I only need to count up to 11. I've drawn 10 electrons, so electron number 11 is here in energy level 3. So I've drawn 11 electrons across energy levels 1, 2, and 3, and this represents sodium. You can see that sodium has just 1 valence electron when I said that atoms were most stable when they had 8 valence electrons. So sodium doesn't have a stable electron configuration, and we see this in nature that sodium is a very reactive metal. Potassium, you can pause the video and try to do this one yourself the same way that we just did with sodium. Potassium has 19 protons and therefore has 19 electrons if we're drawing the neutral atom. And we draw 2 in the first energy level, 8 in the next energy level, 8 in the next energy level, and that adds up to 18. So 1 electron in the 4th energy level for a total of 19 electrons. If you notice, sodium and potassium both have 1 valence electron, 1 electron in the outermost shell. For potassium, that was the 4th energy level. For sodium, it was the 3rd energy level, but they both just have 1 valence electron. This is the feature that gives sodium and potassium their similar chemical properties. They both react extremely vigorously with water. They can catch on fire or release gases that catch on fire. And that super reactivity is true for all elements in group 1 because everything in group 1 has just 1 valence electron. So fluorine has 9 protons, so it should also have 9 electrons. As before, 2 electrons fit in the first energy level, and I don't need to fill up the second energy level because if I put 8 here, that would bring us up to 10 valence electrons, and I only need 9, so I'm going to just have 7 valence electrons in the second energy level. So fluorine has 7 valence electrons because it has 9 electrons total, 2 in the first energy level, 7 in the second energy level. So using the similar reasoning but without drawing the picture, try to reason out how many valence electron chlorine would have. So chlorine has 17 electrons total, and if we have 2 in the first energy level plus 8 in the second energy level, that takes us up to 10, so we only need to have 7 electrons in the third energy level, and we're done. We see that we once again have 7 valence electrons. Like the pattern we saw for group 1, this is true for all elements in group 17. Every element in group 17 has 7 valence electrons. And in fact, in general, there is this pattern of valence electrons that is very simple and straightforward. You don't have to calculate it every single time. It's very easy to just memorize. Any element in the same group has the same valence electrons. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in 13 has 3 valence electrons, then 4, then 5, then 6, then 7, then 8. The one important exception to this rule is helium. Helium does only have 2 valence electrons. So in some regards, you can almost think of helium as belonging over here where the notch has been cut out of the periodic table. However, because it has a full valence shell already, it acts like these other noble gases that have a full octet and are not reactive. It has a full valence shell, so it is not reactive. So helium we write over in group 18 because it's so chemically similar to those other elements. This is an important pattern to memorize. Valence electrons determine reactivity and lots of other important properties of an element, so please do commit this to memory. We're going to skip the dip when looking for patterns in valence electrons and ion charges. That's because transition metals can have variable ion charges. They're what we call multivalent. Their valence electrons get complicated beyond the scope of Chem 1, but so we'll just not memorize a particular number for elements that are in the transition metal zone. I hope this helps.